All right, coming to you from Chapter 9 of the P-5010, your Manual for Preventive Medicine. This is a presentation on preventive medicine for ground forces, and this is going to be focused on the water section of this chapter. Kind of a big chapter. This presentation will just be on the water aspects. First, let's talk about why we got to sanitize our water in the field. So untreated water can lead to a lot of diseases. It can lead to things like cholera, it can lead to typhoid. We can get paratyphoid fever, we can get viral hepatitis, we can get gastroenteritis, and all sorts of parasitic diseases. Parasitic diseases like amoebic dysentery or giardia or schistosomiasis. You get these blood flukes right here circulating in you if you don't treat your water. Responsibilities. Who's responsible for what when it comes to water? Our unit commander. Well, unit commander, he's got the ultimate responsibility to make sure that everybody's got sufficient of quantities of safe water. All right, so unit commander responsible to make sure that everybody has sufficient water. He ensures that personnel are familiar with the dangers of consuming untreated water and know the proper methods for disinfecting their personal water. Ultimately, it's going to fall on the unit commander. Responsibilities of the engineers. Well, your engineers are responsible for providing sufficient potable water to the population to be served. They are responsible for selecting the source of raw water. They got to select where we're going to pull this water from in order to disinfect it. They're responsible for the construction, operation, and maintenance of all structures and facilities that are going to be used in the collection, treatment, and distribution of potable water. So they're going to be responsible for the equipment that's pulling the water out of the source, the equipment that's going to disinfect it and make it potable, and also how it's going to be distributed. That's the engineer's responsibility to maintain those systems. Treatments usually going to include one or more of the following processes: coagulation, filtration, sedimentation, and disinfection. They're going to also be responsible for operating and maintaining all water control points. Responsibilities of the medical department. Well, medical is going to have to advise the commanding officer on all water quality issues. They're going to assist the engineers in selecting a water source. They're going to survey your potable water system. So we're going to be testing it. The engineers are going to be maintaining it. We're going to be testing it. And one of the ways we're going to test it is we're going to conduct routinely bacteriological examinations of the potable water supplies, and we'll get into that in this presentation. And we're also going to be testing for the halogen levels and informing the engineers when the water quality and type of the engineers of water quality and the type of treatment required. So when we say testing for halogen levels, all a halogen is a period on the periodic table, a group of elements, and this group of elements, the halogens, we find them very often used to disinfect water, like fluorine. You've probably heard of water being fluorinated. Chlorine, that's pretty common, and we'll get into that. Bromine, we won't talk about bromine so much in this chapter, but they talk about bromine in chapter 5 when we're talking about water treatment aboard ships, water treatment afloat. Iodine, these are all commonly used to disinfect water. These are the halogens on the periodic table. And then the responsibilities of our personnel. Well, personnel, they've got to be familiar with and follow proper water discipline. And the way they're going to do that is by consuming water that has been properly treated. Make sure they're not consuming, or they're responsible to not consume water that's untreated water. And they have to conserve and protect the potable water that's already been treated. Sources of water, where we can pull water to get it ready for consumption, to make it potable. So all water sources in the field should be considered unsafe until they've been evaluated and approved by medical. Medical's got to give the go-ahead before we consume any water that's sourced in the field. When choosing a raw water source, we've got to consider the following: the quantity, the quality, and the accessibility. So with quantity, we've got to ask the question: will the source provide adequate supply of potable water for all hands for the expected length of stay? So we're going to have to know a little bit about the operation or about the mission, how long we're going to be there. We've got to know how many personnel. We have to have a good estimate on what their water consumption is going to be so we can evaluate and make sure we have enough quantity of water. quality. Well, we want to make sure that the water is free of contamination like sewage or toxic elements or chemical, biological, or radiological warfare agents. We've got to ask, is this water going to be objectionable, right? Are people going to not drink it? Although it's not contaminated, it might be turbid, or it might have an odd color to it or a foul taste. Is it protected from possible contamination? And can it be treated with the resources on hand? So, okay, so is the water, too bad, too contaminated for us to even treat with the resources we have? It just wouldn't be possible with whatever unit we bring to the field with us. And then accessibility. Can we get to it? Okay, can we get to it? And can whatever we're using to purify the water get to it? Or if we need to transport it somewhere, can our transport equipment get to the water? Is it accessible to us? Potential sources are going to include existing public water, surface water. It's a good picture of Crater Lake up in Oregon. Groundwater, like this well here in Afghanistan. Salt water, like the ocean. And then other, which will include rain, snow, and ice. When it comes to existing public water, we've got to consider that it's the easiest and in most cases, the safest source because it's likely been treated to some extent. Okay, so we can't assume that it's safe, but a lot of times, anywhere you go where there's a public water system set up in a place, it's received some sort of treatment. But regardless, we still need to evaluate it, right? Medical still needs to evaluate it and make sure that no additional treatment is required. Surface water. Well, surface water can be more accessible than other sources. It's capable of supplying adequate quantities a lot of the time, especially if you're by a lake or a big pond or a river. The quality can be a problem. In lakes and ponds, when we are getting that's going to be our raw water source. Excuse me. When that's our water source, we got to make sure the intake, right? Whatever apparatus we're using, the big hose that's going to bring the water into that apparatus, we got to make sure it's as far away from the shore as possible. We want it towards the center of the body of water. We don't want it right there on the shore, and we don't want it too close to the bottom, and we don't want it too close to the top, because a lot of debris floats on the top of surface water, and then of course the bottom is going to be all muddy and all sorts of junk down there, and we don't want that to be brought into the intake, into whatever we're using to purify our water. Right, with groundwater, it's usually less contaminated than surface water. But it's difficult to determine the quantities, okay? Because it's underneath the ground. These are wells or underground springs, excuse me. So it can be difficult to get a good idea how much is there, so we can't estimate the quantities. And then we also got to make sure they're located at least 100 feet from all existing sources of contamination and situated so that drainage is away from the well or spring the underground spring. All right, well, with salt water has got to be desalinated, right? We've got to get the salt out of it. We can't consume salt water, and then it's got to be disinfected. To desalinate it, right, to get rid of the saline in it, we've got to, a lot of the times we're going to use what's called a reverse osmosis water purification unit, or your ROPU, and we'll get into that more in a second here. And then other sources of water, rain, snow, or ice, they still require disinfection. You can't just collect rainwater and drink it. It still needs to be chlorinated, or we still need to use iodine, and we'll get into how to do that in a little bit here. All right, a little bit of review here. Who is responsible for advising the commanding officer on water quality issues? Who is responsible for advising the commanding officer on water quality issues? That's going to be the medical department. Who is ultimately responsible to ensure there are sufficient quantities of safe water for personnel? Ultimately responsible to ensure that there are sufficient quantities of safe water for all personnel? Well, that's the commanding officer who's ultimately responsible. Which water source is usually the easiest and the safest to access? Which water source is usually the easiest and the safest to access? Your public water systems. A lot of times it's easier to get to the public water systems, and they've already been treated, but they still need to be evaluated by medical. Which water source is usually less contaminated than surface water, but it's sometimes difficult to determine the quantity, All right, so it's usually less contaminated than lakes, rivers, and streams, but it's harder to get an idea of how much we've got, and that's going to be your groundwater. Moving on to water treatment. The process of purifying water to make it potable may include aeration, coagulation, flocculation, and filtration to remove suspended solids. And then we're going to do reverse osmosis to remove suspended and dissolved matter. Okay, so your big stuff is going to get removed from the water by the process of aeration, coagulation, flocculation, and filtration. But then to get some of the dissolved stuff out of the water, then we're going to use reverse osmosis. And we'll talk about this in a bit, but we got to remember, even after we've removed the dissolved matter, we still have to disinfect the water afterwards. Okay, so reverse osmosis, the two main units that the two units that are covered in this chapter anyway, are going to be your ROPU, your reverse osmosis water purification unit, and your ladder. Your ROPU, right, is the most common field purification system in use. All right, most common field purification system in use is your ROPU. It will produce potable water from fresh, brackish, or seawater. And brackish water is just water with salt in it, but just not as much salt as like in the ocean, you know, seawater. The water is still needs to be disinfected, like we mentioned, after the reverse osmosis process. It's going to get most of everything out of there, but we need to disinfect it for viruses. And not only that, we're going to put, and we'll talk about chlorine in a second here, but we need chlorine in this water just so it doesn't become contaminated in the future. To prevent it, you know, if bacteria gets in it, that chlorine will work against that bacteria. All right, and then your ladder. Your ladder is a transportable, quick response water purification system that is capable of aerating, clarifying, filtering, and disinfecting contaminated water. And you're going to see the ROPU more often. I've never seen an ladder ever used, but I've seen the ROPU before. It's still out there. ROPU, most common. All right, here we got a picture of a ROPU. Right, pulling seawater right out of the ocean, desalinating it, and then it's going into the bladder here. And then your ertolator. I couldn't even find a current picture of one. This is from like a World War II article. All right, so moving on to disinfection. So disinfection, this is how we destroy harmful organisms like pathogenic viruses, bacteria, and protozoans. The most common method of disinfecting potable water is chlorination. Okay, the most common method of disinfecting water is chlorination. As we saw, there's other methods like bromination using the bromine. You'll see that a lot of times on ships, but it's in the field. The most common method of disinfecting potable water, chlorination. Chlorine is added to potable water to reach a desired free available chlorine residual after 30 minutes of contact time. So I'm going to talk about what that means. All right, this FAC, free available chlorine. So we add chlorine to water. Right off the get-go, that water is going to have a chlorine demand. It is just going to use up some of that chlorine. Okay, what's left is going to be called total chlorine. Okay, that total chlorine is going to combine with any kind of organic material that is in that water, because a lot of times water, especially when we get it from the field, is not pure. So that some of that chlorine is going to be just used up by the water, right? That's the chlorine demand of the water. But we also, if there's things within the water, it's going to combine with those things and neutralize them. Like if there's some sort of, some bacteria and stuff or some viruses, it'll neutralize those viruses. What's left is a residual, okay? That's how much. So when we go into testing the water for chlorine, what we are testing is the free chlorine, the chlorine that is still active in that water. So if that water is contaminated by something, it is there to fight against it. So that's what it means when we say we're measuring the free available chlorine, the chlorine that is in that water to potentially help keep it protected. All right, we've got three methods of chlorination we're going to cover. We're going to talk about calcium hypochlorite, or HTH, sodium hypochlorite, and that's your household bleach, and chlorine gas. Your HTH, or your calcium hypochlorite, well, this is usually comes in 65 to 75 or 70% HTH. This is the preferred agent, okay? So calcium hypochlorite, HTH, is the preferred agent because it comes in that granular form like we saw in that previous slide. And it's got a long shelf life, and it's readily available in the Navy stock system. It comes in 100-pound drums, it comes in 3.17-pound containers, and it comes in 6-ounce bottles as well as 1-gram ampules. Our sodium hypochlorite, well, that's 5 or 10% liquid bleach. We can use this instead of HTH, so it can be used in lieu of HTH, but it's less convenient to handle. All right, it's much more inconvenient, much more burdensome to have this liquid bleach, in our supplies than this dry granules that we can store on the shelf. So it's less convenient to handle, and it takes larger quantities to achieve the same concentration of free available chlorine in the water, and it has a shorter shelf life as well. Chlorine gas, we're not going to see that in the field setting, okay? So this is what's, used to disinfect waters, in the city water treatment, okay? So this is what's going to be used in municipal water treatment plants. And it's also not, it's not considered appropriate for field use. The procedure for using calcium hypochlorite. All right, so first, you're going to make a small amount of HTH concentrate by dissolving a measured amount of HTH granules in a clean container. All right, so what you would do is you would look in your manual, in your Chapter 9 manual, and you're going to see it's got these tables so you can calculate the free available chlorine you need for your container. So say that our container is 5,000 gallons. All right, we got a 5,000 gallon container, and we'll talk about how we determine how much chlorine to put in it, but this is parts per million. But say in this container, this 5,000, it is appropriate for us to get our chlorine level to 5 parts per million. Well, that would mean we'd have to take 5 ounces of HTH. We'd take 5 ounces of the calcium hypochlorite. And at first, we're not going to just dump it in this 5,000 gallon container that we're using. What we're going to do is we're going to take a bucket or a canteen cup, and we're going to dissolve that 5 ounces of granules in there and have this super concentrated, chlorinated water. And then, right, well, first off, let's talk about what we do with that. So when you make that concentrated amount, right, not all the granules are going to dissolve. Okay, just allow them to settle to the bottom of the container. Because you're only going to add the liquid to the water that you want to disinfect. So after you've got that concentrate and you've let the granules settle to the bottom, you're going to pour that concentrate into the water to be disinfected now. Now you'll pour it into that rest of that, like we were showing on that chart, the rest of that 5,000 gallons. Provide sufficient agitation, and the best way to do that, to stir the water around, is to add that concentrate when your water container is only partially filled up, and then you fill the container to the rest of the way after that. And then finally, you need to read and measure the free available chlorine 13 minutes after adding the chlorine, and that should be at or above the required dosage. And we'll talk about dosages on these very next slides. So required residuals of chlorination, or the required free available chlorine we need. First, let's talk about the sources of water. So we're going to talk about public water of questionable quality, public water system that we don't quite trust it. Engineering water points, water tankers, bladders, and cans, distribution systems, and then lister bags and canteens. When it comes to our public water of questionable quality, what we're going to do is we're going to chlorinate that water to reach 5 parts per million of free available chlorine after a 30-minute contact time. So that means we would take that public water that we don't trust, we would add enough chlorine to get it to 5 parts per million, and it's got to stay there 30 minutes after we've gotten it there. Okay, so put enough chlorine in there to make sure it would reach that 5 parts per million, and then test it 30 minutes after, and it's got to be at that. Okay, so once you've done that, after that, you just need to maintain, all right, from there on, 2.0 parts per million free available chlorine throughout that distribution system. Engineering water points, like right here, we got a picture of a ROPU. at the engineering water points, we want to maintain a 5 parts per million free available chlorine at the sandpipe or the fill hole. Okay, so right here, where this water's coming in, coming out of this, we want 5 parts per million free available chlorine. Water tankers, bladders, and cans, like these big old water bladders right here. In these, we want to maintain between 5 parts per million and 2 parts per million free available chlorine when they are filled at an approved engineering water point. Okay, so if they are filled from that ROPU we just were looking at, we want to maintain between 5 and 2 parts per million free available chlorine. Distribution, maintain 5 parts per million free available chlorine when it is a source for distribution. Okay, so if if we had a tanker, or if these bladders were going to distribute water to, different piping and stuff, that bladder needs to be at 5 parts per million. All right, a distribution system. At the distribution system source, like if it was that bladder, it needs to be 5 parts per million. Right, by the time it gets to where it's coming out of the source, out of the spigot, right? So the source would be back here, like we say, we got the bladder right here. We need it at 5 parts per million. By the time the water comes out of the spigot, we'll accept a 2 parts per million free available chlorine at the spigot. Then lister bags and canteens. Our lister bag, this guy right here, right? This is a picture of a lister bag from World War II. A lister bag, it needs to be at 2 parts per million free available chlorine when it's filled from an approved source. If it's an unapproved source, right, if it's questionable source, we need to chlorinate it to 5 parts per million initially and maintain that 2 parts per million after that. All right, a little bit of review of what we covered. What is the most common field purification system in use? The most common field purification system in use, well, that's our ROPU, our reverse osmosis water purification unit. What is the most common method of disinfecting potable water? What is the most common method of disinfecting potable water? Well, that is chlorination. Chlorination is our most common method of disinfecting potable water. What type of chlorine is preferred for field water purification? What type of chlorine is preferred for field water purification? Well, that is HTH, or calcium hypochloride. Calcium hypochloride, HTH. What type of chlorine is in a liquid solution, commonly called household bleach? What type of chlorine is household bleach? Well, that's our sodium hypochloride. All right, moving on with disinfection. Next, we're going to talk about superchlorination. In superchlorination, this is what we're going to do to disinfect water containers and distribution systems once they've become contaminated. Okay, this is how we clean them out. And what we're going to do is we're going to chlorinate the water in that container to reach 100 parts per million free available chlorine, and we're going to hold it in that container for 4 hours. All right, so get it up to 100 parts per million and hold it for 4 hours. During that 4 hours, that chlorine, that free available chlorine, cannot drop below 50. All right, so if it drops below 50, we got to start it all over again. When we are doing this, like if you're superchlorinating to disinfect a water bowl or your water jugs, you've got to mark it, right, with the words "poison, do not drink," and it's got to be displayed clearly on all sides of the container and at all water outlets. All right, let's start talking about water purification tablets, and the most common one we're going to see is iodine. So your iodine tablets, they should be a steel gray color. Steel gray water iodine tablets. If they're yellow or brown, all right, or they stick together, they're no longer effective. They're not going to work. So let's talk about how we're going to use these. So if you got a canteen, you're going to add 2 iodine tablets for each canteen of clean water. All right, we just go pop those 2 iodine tablets in there, nice steel gray color. You're going to place the cap on loosely, and then you're going to wait for 5 minutes. After that 5 minutes, you're going to shake the canteen, and you want it to leak a little bit. You want to allow leakage, right, to rinse over the threading. All right, so you want leakage to rinse under that cap and over that threading around the neck of your canteen. And then after that, you're going to tighten the cap, and you're going to wait 30 minutes before you use that water. So it'll take you a total of 35 minutes. You put the iodine tablets in there, wait 5 minutes, shake it up with the cap on loosely, let the water leak over the threads, then tighten it up. Wait for 30 more minutes. If you have a 2-quart canteen, you would double the amount of iodine tablets, so that would take 4 iodine tablets. And we can also use tincture of iodine. A lot of times that'll come in a 2% solution, and our guidance on that is you're going to use 5 drops for 1 quart of clean water, and if we have cloudy water, we're going to use 10 drops. So 5 drops for 1 quart of clean water, 10 drops if the water is cloudy. Using iodine to purify a 5-gallon container. Well, if we're going to do a 5-gallon container, we've got to add 40 iodine tablets. 40 iodine tablets to disinfect a 5-gallon container, and the procedure is the same. After you add the tablets, place the cap on loosely, wait for 5 minutes, shake it, right? Allow leakage to rinse around the threads and the threading in the neck, and then tighten the cap. Wait 30 minutes before consuming that water. Another way we can disinfect water is boiling. All right, you want to use the cleanest water that's available, and you want to bring it to a rolling boil for at least 2 minutes, and then you got to let it cool down. Disadvantages of boiling: well, it requires fuel. That can be difficult to achieve in the field. It's time consuming, and we don't get any residual substance to guard against contamination. Okay, so we can't really boil a bunch of water and have it ready to go because it's at risk of becoming contaminated. Whereas when we're chlorinating or we're putting iodine, we have a residual of that disinfecting agent in there. So if the water becomes slightly contaminated, it's there to fight against that. But that's not the case with boiling. So all our water containers, we got a little bit of guidance for those. They've all got to be labeled clearly with something that says potable water. The interior surfaces got to be smooth, made of a non-toxic, non-corrosive material that is free of rust and chips. Must not be used for any other purpose. They must be inspected, cleaned, and disinfected when necessary, but not less than monthly. Okay, so we can regularly inspect them and clean them sooner, but we can't do it less than monthly. We got to clean those, disinfect those things. All right, our testing requirements. So we need to determine the free available chlorine residual of all water supply at least daily, okay? We've got to measure the free available chlorine once a day, at least. What we're going to test at the engineering water points. We're going to test all our tankers, all our trailers, all our bladders, all our lister bags, and then when we have a distribution system or we have a bunch of 5-gallon cans, we're going to choose some to be representatives. We don't have to test every spigot in a distribution system. We just need to sample points. But what we want to do is we want to vary those sampling points from day to day. Okay? When we measure our chlorine every day, we've got to make sure that we record that in the medical department water log. We've got to investigate the case of any low readings, because your chlorine usually drops when something's in there, causing it to be used. So we've got to investigate any low readings, and we need to report any significant findings to the unit engineer. Moving on to bacteriological testing. So we've got to test for the presence of bacteria at least weekly. All right, and it's the same thing. All right, you're going to test your engineering water points, your tankers, your trailers, your bladders, your lister bags, and then your if you've got 5-gallon cans or distribution spigots, you're going to pick a couple, right, to represent that system, and you're going to vary the couple that you choose every time you test to make sure you're getting a good sample. Again, you're going to record the results in the medical department water log. But if one of these comes up positive, we've got to notify the unit commander, because there's bacteria in the water. There's a potential for people to get really, really sick. This can affect the unit's combat effectiveness. So we've got to let the unit commander know, because we're recommending that the container in question is secured until it's disinfected. We're going to have to get rid of that water, shut down that water source for the time being, and get that thing disinfected. Positive sample points must remain secure until negative samples are obtained. So if we get a positive bacteria test, right, we've got to keep it secure until we test negative. If a distribution system tests positive, right, we've got to take samples 5 outlets upstream and downstream. So let's say that this is a distribution system, okay? This is a big old piping of water, and this right here is a spigot, right, where water's coming out, and we tested it, and it tested positive for bacteria, right? We do our bacteria test once a week, and this one tested positive. Well, we're going to secure it, right, and we're going to take a sample 5 outlets upstream. So we take a sample up here, and we're also going to take a sample 5 outlets downstream and make sure that we don't have, because what we're looking for is this all contaminated in here, or maybe it was just the spigot that was contaminated. That's why we're doing that. Okay, because this could be an easy fix. We might just have to disinfect this, this spigot or whatever the water's coming out of right here. This is a bigger issue if it's infected, if we've got bacteria in here. All right, so let's review what we've gone over. What color should your iodine tablets in good condition be? What color should iodine tablets in good condition be? Well, they need to be steel gray. Steel gray. How many drops of tincture of iodine would be used to disinfect a canteen of cloudy water? How many drops of tincture of iodine would be used to disinfect a canteen of cloudy water? Well, you need 10 drops for cloudy water. How long does it take to disinfect canteen water? How long does it take to disinfect canteen water? Well, that takes 35 minutes. 35 minutes. What level of free available chlorine must be reached to superchlorinate? What level do we have to get to if we want to superchlorinate something? Well, we've got to get to 100 parts per million. 100 parts per million, and we got to make sure over 4 hours that it does not drop below 50, or we got to start all over again. How many iodine tablets are required to disinfect a 5-gallon water container? How many iodine tablets are required to disinfect a 5-gallon water container? Well, that's going to take 40 tabs. How often is water tested for free available chlorine residual? How often do we test our water for that free available chlorine? Only once a day. Once a day. How often is our water tested for bacteria? How often is our water tested for bacteria? Once a week. Once a week. How long must water be boiled for to disinfect it? How long do we have to boil water for? We got to boil it for 2 minutes. 2 minutes. All right, this wraps up this presentation on Chapter 9, Preventative Medicine for Ground Forces. Just focused on the water part of that chapter in your P-5010, your Manual of Preventative Medicine. Like always, I hope this helps, and keep studying.